Okay, so hi everyone, and welcome to this presentation on the qIND-qCPA in security of CBC, CFB, OFB, and CTR. So I know this probably sounds like a lot of big words, but I'll try to explain them soon. And this is a joint work with Amblard and Aurélien Dupin, which work in Thales, France. So since CBC, CFB, OFB, and CTR are modes of operation, I thought it might be cool to just do a quick recap about what a mode of operation actually is. So suppose you're given a secure block cipher, for instance, AES, and you want to encrypt a long message, like, for instance, an image. We know that as good as AES is, it can only encrypt 128 bits at a time. So the most natural way to proceed, for instance, would be to simply encrypt each block of our message 128 bits by 128 bits. If you're familiar with modes of operation, you know that this yields a very, very insecure scheme because it's not randomized. It clearly keeps patterns in the data. So for the modes we will consider, they are secure with respect to most security notion we can think of. So for instance, the CTR mode works like this. We first select at random an initialization vector, and we will encrypt this initialization vector. Since we assume that the block cipher is secure, that is a pseudorandom permutation, this will give you a pseudorandom string that you can then XOR with your message, just like a one-time pad would work. And then you just have to reiterate the process by each time changing the input to the pseudorandom permutation. And the way it works is just like a stream cipher. It is, you will build a pseudorandom string out of your block cipher, and you will XOR this string with your message in order to encrypt it. Of course, this S here will depend on both the key and on the initialization vector. And this will come in handy later in the presentation. So when we say that the CTR mode is secure, we have to define what secure actually means. So in symmetric key, and in fact, even public key, but classically, the way we assess the security of a cryptographic scheme is via the qIND-qCPA security notion. I will assume here that you are familiar with this notion, and if you recall correctly, in the qIND-qCPA security notion, the adversary is allowed classical learning queries and classical challenge queries. So it is a well-known result and has been proven for years that all the modes of operation that we consider here are secure with respect to this notion. But now enters quantum. We want to give more power to the adversary. We want somehow that the adversary can make quantum learning queries. This poses some problems, and this has been dealt by Bonnet and Zandri in 2013. So this yields a new security notion, indistinguishability under quantum challenge plain text attack, and this strictly gives more power to the adversary. So now that we have this new security notion, we would now want to know what is the security of this mode of operation with respect to this new notion. So this is a work that has been performed by Amblard et al. In 2016, and already we can see that in some cases, there are some pseudorandom permutations that are not quantum secure, and when used with them, CBC and OFB are not secure anymore. But the important point is that for the qIND-qCPA security notion, we do know what is the security of this mode of operation. The problem now is that there are some situations where we might want to also consider quantum challenge queries. There have been a fair amount of work in this direction, notably by Gagliardoni et al. And Chevalier et al. But there is a lot of way to define actually what a qIND-qCPA notion would be. This has been summarized by Carsten et al. In 2020. And so now that we have all these new security notions, this begs the question of what is the security of the mode of operation with respect to this new notion. And this is exactly what this work is about. So let's take just a step back and look at how these new notions relate to each other. So in this diagram, an arrow represents an implication between two security notions. So the qIND-qCPA security notion in the middle is the weakest of all, because the adversary is limited to classical queries, both learning and challenge. On the left, on the diagram, there are the qIND-qCPA security notion. Notably, the P6 is just the qIND-qCPA, the previous qIND-qCPA notion. But the important thing is that the qIND-cPA, the security of this mode of operation with respect to the classical qIND-cPA security notion is well known. By Anand et al., we also know the P6 security. And so now our work is to try to assess the security of these schemes with respect to all the other notions. So since the P10 and P11 security notions are very similar to the P6 one, we can in fact just adapt the work of Anand et al. In order to get the security of this mode of operation. This is a bit boring because it's essentially the same proof and it has nothing original in it. But now we have to deal with the right part of the diagram. And what is interesting is that if for all other qIND-qCPA security notions, they all imply the P13 one. This means that if we can somehow manage to prove that all these modes of operation are insecure with respect to the P13 security notion, which is the weakest of all, then we would have proven that basically they will also be insecure with respect to every other qIND-qCPA security notion. So let's do just that. Let's prove for an example, so for CTR and OFB, which are stream ciphers, that they are P13 insecure. So let's begin by defining what is the P13 security. So just like the qIND-cPA security notion, so the classical one, it is defined via a security game where an adversary A has access to two oracles, a learning one and a challenge one. They can make some queries to the learning oracle, it's like some message M, and the oracle will answer with the encryption of M. This is not shown here, but of course this encryption has to be randomized. And so they can do it as many times as they want. A is simply limited by the fact that they have to run in polynomial time. Other than that, they have no other limitation on the number of queries they can do to the learning oracle. Now, A can do a single challenge query to the quantum oracle, to the challenge oracle. So they will send a superposition of messages to the challenge oracle, and depending on the bit B they have to guess, the challenge oracle will answer two different quantum states. In the first case, they will simply answer the way we would expect a standard oracle to work, so with just the encryption of M. But if B is equal to 1, they will apply a random permutation on the message. So if you're familiar with the qIND-cPA security notion, this is just the real or random variant of the qIND-cPA security notion, except that you are allowed, well, except that, of course, the oracle is quantum, and you are allowed a single query. A is not able to learn something with this query. They have to, at the end of their challenge queries, they have to say, okay, B is equal to 0 or B is equal to 1. So for a stream cipher, so for instance, CTR and OFB, we will prove that A doesn't even have to query the learning oracle. They can simply directly send the challenge query, and they can win with overwhelming probability in this game. So as a recall, a stream cipher means that the encryption of a function is an XOR between the message and the pseudorandom string. So A will send what we call the uniform superposition to the challenge oracle. I don't assume particular knowledge of quantum formalism here. I will introduce like the function A will use, but this is just like a quantum state with a superposition of all messages with equal probability. So if B is equal to 0, A will simply receive the encryption of this message. There is a catch here that we said before that S depends on both the initialization vector and the key. We might wonder whether S depends also on the message, which would be the case in like classically speaking, but here it isn't. S only depends on the IV, and the IV is the same for the whole superposition. So S here is independent of M. If B is equal to 1, however, what will be encrypted is the permutation of M. And so if A wants to win in this security notion, they have to distinguish between these two quantum states. A valid quantum transformation is what we call the CNOT gate, which allows, being given two quantum registers, to put in the second one the XOR between the two. Since we're also talking about quantum mechanics, everything's basically linear. So when A performs this state, with this gate, it will apply to the whole superposition. So if B is equal to 0, A will end up with this state, because in the second register, it will be M XOR S XOR M, which is simply equal to S. If B is equal to 1, however, this is the state they will end up with. So there is a clear distinction between the two, because in the first one, the first two registers are not entangled, whereas it is the case in the B equal 1 situation. So unfortunately, I don't really have time, and I don't think it's really relevant either, to dig into the computation details. But if you're familiar with quantum computing, you can see in the B equals 0 case that if you apply an Hadamard gate on the first register and measure, you will measure 0 100% of the time. However, in the second case, you will measure 0 with probability 1 over 2 to the n minus 1, with n being the total length of your message. So if you use several blocks, this will also increase the probability of winning. This means that A has an overwhelming advantage in winning this game. So clearly, any stream cipher is P13 insecure. Note that apart from the fact that we assume that the encryption function behaves as a stream cipher, we didn't use any property of the encryption function. We also prove two general results, because we have, thanks to Carson et al., 14 different qIND-qCPA security notions, and we basically don't know which one is the best. So arguably, what we might want to do is to have a crypto system that is secure with respect to as many as possible security notions. And so if we have no-go results, just like this one, it can be quite powerful, and it can exhibit some behavior of the security notion. Like, okay, we can't select this one because it has this flow, for instance. So for the qIND-qCPA P5 security notion, we will suppose that the encryption function behaves like this. So parsing this equation might be a bit hard. What this means is that the randomization, because R is the randomization of the encryption. So here, the randomization takes place independently of the key, and then you do something with the key. If this is the case, and if R is also given to the adversary, then the scheme is necessarily qIND-qCPA P5 insecure. A way to visualize this better is just with an example, and this allows us to prove that CBC, the CBC mode, is P5 insecure, because the CBC mode looks like this. Here we can see that the randomization is the initialization vector, and the public function G here will simply be the XOR between the first block and the initialization vector. Since the CBC mode satisfies our hypothesis, our assumptions, it necessarily means that CBC is P5 insecure. Note that once again, we didn't use any of the way CBC works, only the way the randomization is handled. Another general result, which actually generalizes a result from Gagliardini et al., is the one-to-one encryption. So suppose we have an encryption function that takes m bits as inputs, p bits of randomness, and outputs n bits. Then we can find an adversary that will have an advantage 2 to the m over 2 to the n in the qIND-qCPA P8 game. In particular, this means that if the encryption is one-to-one, the encryption will, the crypto system derived from the encryption will necessarily be P8 insecure. So this works for most modes of operation. In fact, it works for every mode we've talked so far. The catch is, and what prevents this result from being too powerful, is that if you add an authenticity tag, it won't work, because the authenticity tag will basically increase the output domain by the security, generally speaking, like some linear function of your security parameter, and so this adversary will only have a negligible advantage in this security game. So to conclude, what we've shown in this work is, first of all, we've adapted Anand et al. Results to all qIND-qCPA notion, and showed that the P13 insecurity, of CBC, CTR, OFB, and CFB. This allowed us to completely characterize the security of this mode. In fact, this is but a pretext to study what the qIND-qCPA notions defined by Tristan et al. Really mean. Because we also found two general results on P5 and P8 security to say, okay, if we have these assumptions, which are fairly reasonable, then we know for sure that these schemes would be insecure, whatever they do. This begs the question of the relevance of these qIND-qCPA security notions. Because, for instance, for a stream cipher, okay, it's P13 insecure, but what did the adversary really learn by winning in this scheme? Classically, it is handled by the fact that the qIND-qCPA security notion is equivalent to the semantic security one. And the semantic security one is more intuitive but harder to work with, but we know what it means to be semantic security, to be insecure with respect to the semantic security notion. Here, the problem is that for the P13 security notions, and in fact for most qIND-qCPA security notions, we don't have equivalent semantic security. So we don't really know what it means to be qIND-qCPA insecure. So if you have to just remember one thing from this talk, one takeaway is that if we want to define an actual useful qIND-qCPA security notion, we have to do more research, either to define a semantic security notion for all of these qIND-qCPA security notions, and we're going to also try to find some relation or some more no-go theorems for some security notions to say, okay, maybe this is not a reasonable definition for security notions. Thank you.
I still don't really understand the rationale for considering models that allow you to make any query in a quantum superposition. Like what world are we conceiving of an attack where that can be done in a way that's not trivial to detect?
This is I think the biggest concern regarding this work. Even for the previous paper, we all have our beliefs on this topic. I think that the most reasonable argument for this matter is that of white box cryptography. Because for white box cryptography, you're given a quantum circuit, and you have to find something about it. Which may happen in, I think it's a fair assumption, and it's a fair assumption, sorry. And if you have a classical circuit that computes your encryption function, then you are able to do a quantum oracle with it. So this is one way to say, okay, if I have a classical circuit, then I can do a quantum oracle, and so I can use these attacks. Another thing is that it may be useful if in proofs of security, even if your primitive is not directly queried quantumly, it may just happen that you need in the proof that it is quantum secure with respect to some oracles. I think these are the two most reasonable arguments for justifying the quantum superposition.
Okay, you showed that the various common modes are does not meet your security notions. Do you know if there actually exists a cipher mode which actually does?
That is secure with respect to the qIND-qCPA security notion?
That's correct.
Yes and no. There is a theoretical construction by Tristan et al. That is both P1 and P2 secure, and if you're P1 and P2 secure, you're secure with respect to every notion. But in order to do this, they have to assume for quantum secure pseudo-random permutation. Okay. If you have quantum secure pseudo-random permutation, that we do know a construction that is secure according to all these notions.
Thank you.
Thanks for the talk. I read this Anand et al. Paper a while back, and if I'm not wrong, they also analyzed this so-called XTS mode of operation. I think that paper, it uses a really weird security notion where the adversary has control over a first half of the plain text, and then the game is to recover the second half. So I'm not sure how that fits in with the new qIND-qCPA security notions for XTS.
So this is an interesting question. The XTS mode has been studied by Amblard et al. In the 2016 article. There are, I think, 2 or 3 reasons why we didn't consider it. The first one is that the XTS mode is mainly used to encrypt hard drives, and it's not sure like what it would mean this time in order to be for it to be quantum created quantumly. Also, I'm not even the problem with XTS, I think, is that we're not even sure that it is secure with respect to the qIND-qCPA security notion. And the final one is that I did this work while I was in an internship at Thales. And CBC, CFB, OFB, and CTR mode are really used in the industry and in communication, and XTS is not. So my supervisor probably thought that it was better not to consider it, especially since, it's in the world of Amblard et al., the XTS mode is being treated like it seems like a weird mode with weird security notion. So this is why we didn't consider it.
Okay, makes sense. Thanks.
Thanks for the time.